The bomb run. A bomber is flying 200 meters a second to the west with the wind heading 50 kilometers an hour to the east. With 6 hours of fuel and the target being 4,800 kilometers away, can they possibly make it? This is a trip to the target, not returning. So the first thing we have to do is set our vector directions. East will make negative and west will make positive. So 200 meters a second is the plane, plus 1,400 meters a second east. In vector notation, we add. We don't just automatically subtract. That will take care of itself. Then we replace the west and the east with a positive or negative sign, and we get the plane is flying 186 meters per second to the west. Now we list our variables to compute the distance the plane can enter. And here is where the misunderstanding comes in. Many students will now set the distance to be 4,800 kilometers. But that is not what you're being asked. You're being asked, how far can you make it? Can you make it 4,800 kilometers? And that's where the mistake comes in. So let's not make that mistake. And the next thing we need to do is convert the hours of flight to seconds. So we've got the plane speed in meters a second and the time in seconds. We calculate the distance flown and we get, at best, they can do 4,000 kilometers. So they run out of fuel before reaching their target. The slightly more difficult one. What would be the farthest target they could reach and still be able to get home? This trip now has to be broken into two phases: the way out against the wind and the way back with the wind. The plane speed on the way out is going to be its speed minus the speed of the wind, but on the way back the wind is going with the plane, so you will take the plane speed and add the wind to it, which is why I've written V plane plus or minus the wind. Are you flying into the wind or backwards? What's with the T naught and the TR? Consider the T naught to be time out and TR to be the time to return. The two distances must be the same. You go from Guelph to Toronto, and at the end of the day, you reverse it. The distances are the same. But if your speed is different, there is no way the times to go out and come back will be the same. But we can make a truthful statement about the time. If you have 6 hours of flying time, then whatever it took you to get out and then come back, it must add up to 6 hours, if that is the limit of your flight. So this will drive our solution, that yellow equation. The two black equations are the setup for motion, but the key critical thing to realize to solve for this is what I've highlighted in yellow. We now have a substitution problem. We cannot solve for two unknown time values with those two equations, but we're going to be able to replace one of these times with this expression. But let's not get ahead of ourselves first. Let's start. Here are our three governing relationships. We have two different times here, and we have an expression that the time out and returning must add up to 6 hours. So 186 meters a second times outbound time must equal the inbound speed and time. The distance you traveled to the target and the distance you traveled coming home are the same. Now we can relate the times to each other. If I take the 186 and move it to the other side, I'm getting that the time going out is going to be a ratio of the speeds. We get that the time going out is 1.15 times longer than the return trip. We don't know the return time, but we now know that it's going to take you 15% longer to go out than go home. And this is what's going to let us find that time. So on this slide, I've just recreated the math from the last slide. There's nothing new here. I just need more workspace. So the critical part is connecting the two time values together. So I'm going to move them up to the top here. Since outbound time and return time must equal 6 hours, and we've found, when I combine this equation down here, get rid of the middleman, we have found that the time going out is 1.15 times longer than the return trip. You can read that as 15% longer. So we're going to substitute. We're going to take the T0, the outbound time in this expression, and we are going to replace it with this equation. And you might go, why would we do that? Because instead of having two separate time values now, we have one unknown. The substitution of one equation in the other has completely knocked out one of the two unknowns, and we easily solve for the time to return. The time to return is 2.79 hours. Now, since the two times have to add up to 6 hours, the time going out, we can just take 6 hours minus 2.79 hours, we get 3.21 hours. Or use the blue expression up here to calculate time out. If you do that, you get some redundancy. You get a double check, but I'm not going to do it. Let's confirm that we're right. The distance going out is 670 kilometers an hour. I thought it was 186 meters a second. No, I converted to kilometers an hour since our time is in hours. Could you have turned the time into seconds? Yes, but by turning this one into kilometers an hour, I have less arithmetic to do. So the distance going out is the speed going out times the time outbound. I get 2,149 kilometers. The D coming back, returning, is the speed on return times the time we calculated right here. We get 2,149 kilometers. So that's their bombing range. Given the wind conditions of the day, they can reach 2,149 kilometers before they have to turn around, and we've adjusted for the wind. Can we do this problem in our head? Well, let's think about it. The plane's actual speed is 200 meters a second, but it's flying in a wind of 14 meters per second. Let's look at that. First of all, is a 14 meter second wind much compared to 200 meters a second? No, so the problem probably won't be very different from ignoring the wind. That wind speed, if we compare it to 200, the wind speed is only 7% of the plane's speed. So think about it this way. Would this not mean that the plane is 7% slower on the way out and 7% faster on the way back? No wind would make the travel time exactly 3 hours. Add 7% and take away 7% to that time. Look what happens when I calculated it. I added 7% to the 3 hours and I took away 7%, which is 93%. So ballparking it, I can say my answer is going to be plus or minus 7% of an equal time, and it actually gives me the answer using my old noodle and thinking. Now, you cannot demonstrate your answer this way on a test, but this is again one of the techniques I'm using in my head to know in advance when I've screwed up my formulas. And you have no idea how many times I screw up when I'm making sample calculations. You only see this when I'm done. Let's move on to a fairly simple one now. The attendance cheetah. The school is releasing cheetahs to encourage prompt arrival. So we want to know, can Ralph make it to the door before the cheetah gets him? And there's a basic rule in horror movies. If you think Ralph is cute, he makes it to the door. If he's the obnoxious character, he's first to die. But this isn't a horror movie. It's physics. I know the two can seem very similar, but this is definitely physics. So what's governing it here? Does Ralph make it to the door before the cheetah? So the obvious thing would be calculate the distance the cheetah has to go and the speed of the cheetah. We get 8 seconds. But when Ralph runs to the door, he only has 30 meters to go. So he will reach the door in 3 seconds. It is a pursuit problem, but I didn't set it up as one. So the question is this sufficient? Is this good enough to demonstrate you could prove that Ralph is going to make it to the door with the cheetah still 5 seconds to go? It depends on what the teacher's asking you, and this is where you ask a question. If it was worth 3 marks, then you're just being asked to do this. If the teacher had bracket 10 marks on this, then they're probably expecting the full-blown setup of D1 equals D2 and all that kind of stuff. But here, no, this would be good enough. The full-blown method would look like this. You would take the conditions of interception, make the two the same, and you get the interception is at 11.8 seconds. So this proves the cheetah would never catch up to Ralph till 11.8 seconds, but Ralph is at the door in 3. Okay, so you might go, well, what the heck? Why did that happen? Well, this would be the cheetah intercepts him if it got into the school and kept chasing. Okay, now you take a good look at that and make sure I'm correct, that I haven't made a mistake. See if it makes you go, wait a minute, isn't that different from the last slide? And do I really need to do this? Right? So this one is just left here as a poser. It's not the solution to the problem. It's just to get you doing a little extra thinking, so feel free to skip it. What about 2 cars racing each other? One is given a head start and one of them is accelerating. So car A, its equation of motion is its 100-meter head start, and since it's only accelerating, we get 1/2 5 meters per second squared times time squared. There's no starting speed for car A. All right, so this car is starting from rest, but it has a 100-meter head start and it has an acceleration of 5. Car B starts at 0, but has only a constant speed. It doesn't accelerate. So the question is, will vehicle B ever catch up to A, or the reverse? Well, first of all, which one of these equations is going to dominate? Which one is going to win in the end, no matter what? An equation that has a straight multiplier or an equation that has a power on one of the numbers? Can you not see that eventually this equation for dA, as time goes up, is going to take off like a rocket? This equation is going to respond a lot more swiftly to the time value than this one. So let's take a look. Here's a brute force method you could use. I used Google Sheets and I punched in the 2 equations. Obviously you cannot put units in, and I plotted the 2 equations, and what it looks like is car B took off at a constant speed of 50 meters a second, but car A, there's his head start, 100 meters, and he started to move, and then he really began to take off. So what this means is car B caught up to car A right here just after 2 seconds. Do you see that? But car B is constantly traveling. Car A is gaining speed. So car A was going, and car B went boom right on by. But does that mean car A will always be left in the dust? Do you see what's going to happen? How many seconds before car A will be matching the speed of car B? What do you need to multiply 5 by to make it reach 50? Can you do that in your head? What number squared will be 10? Well, I don't know. Let's think about it. If I put 3 seconds in here, that would be 3 times 3 is 9. That would be 50. So in only 3 seconds, this car is going to match the speed of car B. So I think car A is going to catch up again. I think there's 2 solutions to this one. Okay, so we have an interception there, and the question is there going to be another intercept? By examining the shape of the graph in that formula, do you think car A is eventually going to win? Well, let's see. The condition for an intersection or an interception is that the 2 meet at the same point in space. So this means dA will equal dB. We put it together and we get this formula. We collect like terms and it will collapse to this quadratic. At the point we add the quadratic in, just drop the units. Do not keep them. It will make a mess out of things. So this is the one kind of problem where you're allowed to drop the units. Now, why do the quadratic if I can reduce these numbers first? So I can reduce 100, 2.5, and 50. I can factor them down to 2.5, 50. Sorry. Now I take these and I rearrange them in quadratic form. 2.5 t squared minus 50 plus 100. Why would I keep them that way when I can divide everything by 2.5? So I do that and I reduce the quadratic to much easier letters to solve. So we move to our solution. Here's the quadratic we've got. A is 1. B is negative 20. C is 40. This leads to 2 solutions. 20 plus this and 20 minus this, and both of them give us positive time values. So in fact, car A is finally gonna smoke car B 17.5 seconds later, even though at first car B won. So here's a case where the 2 solutions of the quadratic make real world sense. We didn't get a negative time. We got 2 times, and what you have to see it is what it is. Here is the plot of those 2 curves, and you can see the intersection at 2 seconds, and then the car accelerates. The problem I goofed on is Desmos reversed the colors on me. So this was the blue line in the last one. So just look at it this way. The vehicle with constant speed momentarily blew past the one that had the head start and was accelerating, but the one that's accelerating eventually started to gain so much speed it caught up with the other one. How can we tell it's going faster? The slope of the blue line is less than the slope of the red line here. Down here, the slope of the red line is nearly 0, but the slope of the blue line remains constant. Now, I've made a funny alteration to this graph. When I plotted the numbers, this graph is stretched so vertically it's unreadable. So this is an acceptable technique. I divided both equations by 100, and that caused it to squish the graph down vertically. So I could show you this interception. So these numbers on the side are 100 times bigger. This is an 8, it's 800. Now, does that screw up what I'm seeing? No, it does not. I squished the vertical axis. I did not change the horizontal, so that 2.5 seconds and 17.5 matches the quadratic completely. So you are allowed to do that to multiply or divide one of the axes to make the graph more readable. You just explain you've done it. Okay? So we have the red line is almost stationary at start, and the blue line is just clocking away. And the red line had a head start, but very quickly, within 2.5 seconds, the second vehicle catches up. But then later, because this red line is showing acceleration, eventually the first car catches up and beats the other car. And that other car will never ever catch up because it's at constant speed. See me if you don't understand this. Now, the next problem is called playing chicken. And as you know, playing chicken is running at each other. So this is a simple collision problem. You can go back to slide 9 of the Kinematics Ninja in C. But I'm giving you an acceleration of a chicken. Chicken 1 is at 2 meters a second, and it accelerates at 2 meters per second squared. And that's actually a valid value for a chicken. I looked it up. First confusion. 2 meters a second and 2 meters a second squared. Aren't they the same? Numerically, they're the same, in the same way that 2 chickens and 2 cows are numerically the same, but they're not identical. You don't go, 2 chickens, can I just substitute 2 cows in for it? Yeah, if you give me an extra $10,000, do you know how much the cow is worth? I'll sell you the chicken for $20, but I'm not selling you 2 cows for $20. They're different. So it's very easy sometimes if you get identical numbers on the measurement to think you've got 2 identical measurements. Right? $20 and $20 an hour are not the same thing. Okay? So I try to avoid doing that, but at the same token, you do need to realize that, or you can get confused. All right, so we set up our 2 equations of motion. Accelerating chicken on the left, constant speed chicken on the right. Unlike the previous problem, there is no head start for anybody here. But the first chicken has a constant speed as well. He starts with, so there's a VIT term that wasn't in the last example. So we put this through our pipe, and when we recollect all these terms, you're going to get a quadratic that 100 equals 2t plus 4t squared equals t squared. You rearrange, and there's your values, 1, 6, and negative 100. You put it in the quadratic, you get 7.5 seconds for the chickens to collide. And when you do that, you can confirm. D1 is 71.25 meters using this time. Chicken 2 travels 30 meters. Add the 2 up and you get approximately 100. Why is it different? This quadratic equation is twitchy. Any rounding whatsoever, when you do it, will throw the answers off. If you did the quadratic exactly and you carried like 4 more decimal places on your time, you'd get the same answer. Okay? So this would be a must be able to do this one. All right? I want to see you be able to do a collision problem or a pursuit problem where the full-blown quadratic shows up. Now, supposedly Galileo dropped objects from the Leaning Tower of Pisa, which is 56 meters tall. How long would it take for the thing to fall? Well, first of all, he never did it. Or if he did it, it wasn't due to science. I think he may have actually done it because he was participating in the art council in Pisa, and they wanted to improve the quality of the street art. That's what I've been told anyway, that it was an art restoration project to improve the caliber of the street performers in Pisa, which is why he dropped the ball. Anyway, this seems like it's easier than the other ones, but that's the point. What happens again is if I stretch you to a new limit, then I give you something easy again, you suddenly go, I can't do it, because you're thinking that it's got to be, whoa, it has to use the quadratic now. No, it doesn't. And so this is very normal if I retreat a little bit, that you suddenly go, I can't do it, because you're thinking just on the current material. So this one turns out to be fairly straightforward. You summarize your variables. You can use G instead of A when it's gravity. And you keep your distance in there, or the direction. And there be basically one way to solve this one, using D equals VIT plus half AT squared. But are we going to be able to avoid the quadratic? Yes, actually, because there is no initial speed. When you drop something from the roof, it starts off at 0. What happens if we deliberately threw it down? That comes later. But right now, we lucked out. The quadratic's not going to show up. And we get this rearrangement. And you're like, holy moly, that's easy. I can do that. And you put the numbers in, you keep your units. And when you're done, you get 3.3 seconds. So 3.3 seconds for it to fall down the tower. Now, could I verify this in my mind? Yeah, let's think about it. Gravity's roughly 10. So if you fall for 3 seconds, you will reach 33 meters per second. The average of 0 and 33 is around 17. I'm going to make it 18 because it's easier. 18 meters a second for 3 seconds is going to be 18, 36, 54 meters. So in my head, I just look at it and go, 33 seconds, I'll put you 33 meters per second. That's roughly 18 as an average. 18 times 3 is 54 meters. Oh, yeah, it worked. So do I expect you to do that? No, how on earth would I mark what I just said? What I want you to be able to do is start looking at these numbers and playing around with them, not being terribly frightened. You want to start getting good at what you're doing. You want to start finding it like kind of relaxing and easy. This is Perry's International Victory and Peace Memorial from the War of 1812. It's this large Doric, not dork, Doric column in the middle of Lake Erie where the Americans can see a spot on the water that they won. It's a very narrow island. Like there's water here, and at this point, if you walk across here, just at a view, well, actually not at a view. Do you see this little cement line here? That's the other side of the lake. Okay, lake here, walk through the island, lake there. You see the people down here? It's not very big. It's like football field. And I used to go on Ranger Exchange for 1 week each year where I got to be the British soldier from the War of 1812. And one of the most noteworthy questions I would get on the steps of the monument would be, an American would say, if this is Lake Erie out there, what's that lake on the other side? You are in a place called South Bass Island. And that was number one. Well, this is Lake Erie, what's that one? And I would say the Atlantic Ocean, and they would say, like, I didn't know he'd gone so far east. So it was really odd. I call it Drunk Boater Island. Most of the visitors to the tourist site were drunk. And over here is Stone Lab. It's a biological lab studying Lake Erie, and it's really cool. The place wasn't being used at the time, so the girl I was working with, she was a biologist, and I had this gigantic old like Victorian lab to play around, and it was really cool. But anyway, one of the bizarrest tourist things of all is this bloody rock that was knocked off by a bolt of lightning, hit the basement, hit the floor, crushed a woman to death, and then continued on with her body into the basement of the unknown soldier. And they have it on display in the gift shop. It's like, yeah, that's the rock that killed her. So it's like, it's kind of weird. So this is exactly the same problem as before. But sometimes when it gets made specific, you can't do it again. Once again, we have a slight difference. Now, we've got 107 meters and gravity. That's all we've got. What do we do with that? Well, without the time to fall, we just need this equation here. And then we can work out that since it's starting from rest, we have a 0 starting speed. We plug in our numbers, rounding gravity, because I just don't see why we would bother with it exact. And you would get 46 meters a second when that rock hit her. Now, is that a lot? Well, if 28 is highway speed, this is a lot. And it's a big chunk of rock. It's like the size of a desk. You know, like not a school desk. I mean, like a sit-down drawers on either side of you desk. It's a big chunk of rock that hit her and drove her right through the base of the monument. So, yeah, you would definitely not survive that fall or survive something falling on you from that monument. Another one is the HARP gun. And this is the same problem now as the last two, but it's reversed. We're throwing it up. You know, the gun's going and it's throwing the shell upwards at 2,200 meters a second. How far would such a shell fly? Well, it's the same problem, just going backwards. And once again, you have to realize you're being asked to calculate D, right? And T if necessary. I'm going to calculate both. So we've got two unknowns. And so we can't solve for both of them at the same time. So no equation that contains both distance and both time can be used out of the gates. We can only use an equation that contains only one of D or T. There can be only one. So the easiest one is to use the VIF squared one. You state the formula, you rearrange it, and you track these carefully. The brackets go around everything and you square it. Why did the minus stay outside the brackets? Because it's right here. Okay, it's right there. It's not inside the term, it's subtraction. Where did the VF go? Why did the term just vanish? because it's going to stop, right? When a bullet goes to its maximum height, it's going to stop and turn around. So when we're done, this calculation leads us to 242 kilometers. Okay? Now, according to our calculations, this shell, to go up to 244 kilometers, we would calculate A equals delta V over T, rearrange delta T equals delta V over A, and you get 37 meters in one direction. Minutes. Now we're looking at the stunt jump problem. What minimum speed would a car have to drive and leap a 10-meter jump to a building 8 meters lower in height? Nothing is difficult here other than deciding what is the governing factor. And that has to be the falling time. How long does it take an object to fall 8 meters? Why is this the key? Because if you jump, by the time you've lost 8 meters, that's when you want to be at the other building. Let's suppose you didn't reach the building and you had fallen 8 meters. Now you plunge to your death. What happens if you were past the building before you fell to 8 meters down? Then you miss the building to the right. You fall to your death. You need to time it so that you are where the building is exactly at the moment you fall in 8 meters. That's what's governing the problem. So we take the distance in the vertical. Our initial speed in the vertical is 0. We're not concerned with the final speed, and our acceleration is 10 meters per second squared down. Since both D and A are downwards, we can ignore the sign for this problem. And we get, fortunately, a situation where the quadratic disappears. Because the VIT term is 0, we're just left with D equals 1/2 AT squared. Rearrange, and we get time is the root of 2D over A. And that leaves us approximately 1.26 seconds to fall to the next building. Does this make sense? Well, think of it this way. When you fall for 1 second, you will reach 10 meters per second speed. That leaves you an average speed of 5. 5 meters a second for 1 second is a fall of 5 meters. So 1 second would have you drop 5 meters, so it's totally believable that 1.2 seconds has you fall for 8 meters. Now that we have the time, the car must be there. It's got to be over that 10 meters, so it is at the building when those 1.26 seconds expire and it strikes the ground. So we have a 10-meter horizontal jump. We're going to have a constant speed we need to calculate, and we have 1.26 seconds to be over that building, so we land on it at the exact moment we fall in the 8 meters. And we get 8 meters a second will carry us over to the other building just in time for our wheels to touch down. So what we want to know, is this the minimum speed, the maximum speed, the ideal speed? What would you call this? Okay, in order to do that. So this one, it's not hard math, but it's tricky to get the conditions set in your brain to decide what it is you need to calculate first and what's determining success on the jump. Let's take a look at the landing. It's not a question I asked you. This is going to be a little bit of like just watch and learn. We're going to figure out what kind of impact speed the car had. So step 1, we need to figure out the vertical speed. Given that we know the fall is 8 meters, and without the time, we could use the time. We calculated it in the last slide, but it's always better to avoid using a calculated value. So without the time, we could calculate the vertical speed to be 13 meters a second. We already know the horizontal speed is 8 meters a second. So if we combine them using Pythagoras, we get 15 meters a second for this resultant speed, the blue line. Notice how careful I was with the double bracket so I didn't make any goofy mistakes when I was compiling everything together. Does this tell us the impact speed of the car? Yes. But where your brain is going with it, well, is the car going to land nose down? Is it going to land on its front wheels, rear wheels, or all four? The situation will get really complicated beyond high school. So we're going to assume that they trimmed this car perfectly and it lands with all four wheels on the ground. So it's going to hit at 15 meters a second. Is that safe? Heck no. 15 meters a second is 58 kilometers an hour on a drop. So how is that going to feel? Well, let's take an idea. The car is likely to stop in about a half a meter. Why did I pick a half a meter? That's going to be its best, easiest stop. Most shock absorbers on a car do not compress more than a half a meter. That's a really big travel. So the car is going to go and squish down on the ground, and it'll squat on its suspension half a meter at best. Like, this is really the car breaking up pretty bad. So this guy is lucky if he gets a half a meter to come to a halt. In reality, the car might hit and come to a vertical halt in only 30 centimeters. But let's work out with half a meter. We do the math on this, and we get his deceleration is going to be 170 meters per second squared. And that's 20 Gs. You're going to feel like, on your bum, imagine being turned upside down and having about 8 sumo wrestlers simultaneously dropped on your butt bones. Or think of it this way. What if we held you and dropped you onto a chair, except there were 19 clones of you sitting on your shoulders? A 20 G impact to the base of your bum when the seat hits is likely to paralyze you. So in the notes underneath this screen, in the speaker notes, there is a clip from the movie The Punisher, which shows them doing a jump that is not nearly as high as the one I've calculated here. And I've queued it up to the correct spot, and it will show you the lengths they had to do to protect the driver from that sudden deceleration of the vehicle on the vertical, striking his spine and putting him in a wheelchair. You don't have to watch the whole 12-minute video, but I would like you to go to the notes or in the links below this video and watch that scene from Making of the Punisher and see how they avoided a brutal deceleration on the guy's spine for the car. And this should tell you how realistic it is to think as a young teenage male, because girls don't do this, that you could get in a sports car and try a jump like this and walk away from it. I try to make my slides so they're animated when I teach, but they can be readable when they're just looked at as notes. But sometimes I can't do that. So on this slide, that's the case. There is material here, but it's under boxes that are the same color as the background. So if you view the slide itself, it will look empty, but if you click on the space, you'll realize there are boxes that will fall out of the way, revealing the steps one at a time. So what if we wanted to come up with a general statement to go like, I want to be able to put in any speed, any distance of gap, any drop. Could we make up a general statement that we could use over and over again instead of constantly recalculating? And so we're going to go for a pure algebraic solution here. This would be something I would really like it if you could do, but you could get away without it now, but you want to be here by university, okay? So let's say we're going to just drop the car again. So we're going to drop it from a height, and it's going to smack down at a lower altitude. Well, whatever the drop is, we can rearrange this formula, start some rest, and we can get an equation saying the final speed of a car is going to be root 2AD, where D subscript V is the distance you're going to let it fall. So that would give us our impact speed when we do the car jump. But what about the vertical distance we fall? Well, we want to know how long it's going to take the car to fall a vertical distance. That's really critical to move on. So again, initial speed is 0 when we drop the car. It's going to accelerate due to gravity. So if we rearrange without numbers, we get the time to fall is going to be the square root of 2dv over g. Once again, d subscript v is the vertical fall. You could use height, you could use d, it doesn't matter, as long as you keep track that this is the vertical side. Now what about the horizontal jump? Well, this one is much easier. The distance you're going to jump the gap with is the speed of the car times the time you have available. Well, what's the time that we have available? It's right here. It's the time of fall. So I'm going to do a little trick, and I'm going to knock the time out of this equation by replacing it with this expression. And this is what happens. If you put in root 2 dv over g in place of time, we now have this expression in all its glory. The gap you can jump is going to be the speed of your car times the square root of the distance you're going to fall times 2 divided by the planet you have to be on. So this would give us a general equation, not a single example. You could now put in any speed of the car, any distance you're going to allow the car to fall, and it would tell you the maximum gap you could jump. This is why I keep pushing for you to do things with algebra. You would never see this pattern if you used example numbers. Now, this could be something that, say, you worked in the movie industry and you were a stunt coordinator and you were working out the parameters of a stunt jump. And the guy would go, let's say you were the stunt coordinator for a movie. You might go to your trailer, sit down with your physics textbook, and work out what the stuntman needs to do to finish the jump. You don't think these guys just guess, do you? You might have a team of engineers or a guy with some physics training, and he sits down, or he just provides the movie people, use this formula to calculate your jump. And they would give these guys tables, and they would calculate very carefully what they could get away with. So very often this stuff is highly coordinated. Now, did you follow this? If you did, you are a god of some type. For a high school student to follow this kind of rearrangement is at the limits of your difficulty, okay? It's really pretty much right at the end of what you are capable of, but you don't get any better by staying in the safe zone. By next year, you really should be doing this, but by the first year of university in math and physics, you gotta have algebraic substitution under your belt. You really have to get used to playing with the letters, not example numbers. So I introduce this now, and you are probably, I can't say, since you're scattered all over during COVID, what your next teachers will want you to come equipped with. So I would rather go a little overboard. But this would not be a testable equation at this point. I would not ask you to demonstrate this. But if you want to learn how, just start playing with letters and don't put numbers in at all if you can help it. Now the Cindiana Jones, this one's a real challenge. So we have to figure out how long is it going to take her to run 100 meters and what will the boulder do. Now it doesn't matter that she's on a ramp because I've already told you that the ramp has reduced gravity to 4 meters per second squared. And this is hard for me to explain, but I'm just kind of imagining a second ramp that's hidden and it dumps the ball on, except the ball is going up the ramp and turns around. So we're actually complicating things that the ball is rushing away from her first, and then it slows down and turns back. So we have two basic equations. The distance Cindiana is running is easy. It's just her speed times time. But the boulder, I've created a ridiculously more complicated equation of motion for the boulder. The boulder starts 30 meters behind Cindiana. That's the minus 30 meters. The boulder is launched at 12 meters a second up the ramp, but it's going to start accelerating backwards down the ramp due to gravity. And so the boulder's going to go whoop and turn back and chase her. So does she get out? Well, the answer is, how long is it going to take her to run 100 meters? And in that time, where does the ball wind up? If the ball is still behind her, she's safe. If the ball is in front of her, she's screwed. So you can do this as a two-parter, or you can make these two equal to each other, turn it into a pursuit problem, and use the quadratic to get the answer of where they intersect. We're going to do both. So if all you're asked to say is, did she get away, it's fairly straightforward. We find out that Cindiana is going to take 11 seconds to make it to the door. Okay? Now, what happens to the boulder in 11 seconds? The boulder now has 11 seconds to accelerate backwards towards her. Okay? So the acceleration that's positive is to the left in this case. So the boulder is sent uphill, minus 12. So I've established, though I didn't state it so, which is always a good idea, I've established that going to the right is negative and going to the left is positive. Most math teachers do it reverse. It just doesn't matter, whatever you're comfortable with. So we put that into this formula, and we get that the boulder, it starts 30 meters behind her. It's going the wrong way for a number of seconds, but look at it. It's going minus 12 meters a second. Considering it's accelerating to the left at 4 meters per second squared, literally look at this. It's going minus 12, minus 8, minus 4, 0. The boulder's acceleration is going to counteract this speed to the right in how many seconds? 12, 8, 4, 0. 12, 8, 4, 0. By 4 seconds time, that ball will be reversed and heading her way. But it only manages to travel 80 meters in that time. So she's out the door. She's safe from the boulder. But the boulder is accelerating to the left. And as long as she's running at constant speed and the boulder is accelerating, sooner or later it's going to get her. But in most of these movies, like Indiana Jones, the boulder just stops at the door. Like, he runs out of the temple and the boulder just, like, it's gone. So apparently these boulders are under some sort of, like, magic spell that prevents them from exiting the temple of the patriarchy. So we're going to change this one. This stone boulder doesn't stop at the door. It chases Cindiana out. So how long before the boulder catches up? Well, now we would do this as a full-on pursuit problem, and we would make Cindiana's distance equal to the boulder's distance equation, and when the two distances are equal, she is a pancake at the point, eh? And this is what happens, and you're better off drafting it on your own, but we just put in Cindiana's equation of motion, the boulder's equations of motion, and I collect all my terms, and when I'm done, I'm left with a lovely little quadratic, 2 minus 21 minus 30. And then I didn't even bother to reduce it. You know, you would be, well, you can't, can you? You can't divide by 2. So I get 11.77 seconds. So at 11.77 seconds, the boulder catches up to her. Okay? And you're like, oh. So Cindiana Jones only has 0.67 seconds to go, woohoo! I made it! And she's done. In fact, I think she would just go, wait! And boom, the boulder gets her. So yeah, Cindiana Jones lost this one. And by the way, I have trademarked Cindiana Jones. It's my nickname for a character. And what's depressing is most of you are probably like, who's Indiana Jones? Now let's verify Cindiana Jones. You can verify that what I have told you is the truth by plotting her motion and the rock's motion on Desmos. Okay? Now for this case, I didn't put in the rocks. Well, I did actually. Not here. I didn't write the 30-meter head start here. But you can see there's the rock, minus 30 meters, 12 meters a second, and an acceleration of 1/2 times 4. That's the 2, and there's Cindiana running at 9. When I plot the 2, we get the intersection there. And you can see that, again, this plot is stretched very much vertically. So if you wanted to see this in more detail, then you would, instead of plotting these two formulas like this, just put like a decimal 0.1 in front, and it'll go and flatten the vertical axis, and you can have a look. But there she be, 11.77 seconds, right? That's right from Desmos, the intersection. So it doesn't harm you to try it on Desmos, because the more you practice with the graphing programs, the more they become your good friend instead of an annoyance. And it'll really teach you a lot to take these pursuit and collision problems, quickly type them into Desmos, and see if the graphing calculator agrees where the intersections are. I mean, why not, right? I had to do graphs by hand when I was a child, on graph paper, both ways uphill. Let's try another one, a stuntman safety. We're going to break this into two problems. So a decision problem like this can really trip up students because they try to treat it as one problem, but there's a logical division. And learning to spot those divisions in the problem is the key. It's not the math. The math is the same for all of these problems. It's just spotting where the critical decision making is. And I don't think that's generally well explained in the textbooks. That's why it's kind of my duty, my personal thing is to get this. This breaks into two problems. A stuntman's going to fall. And for the first part of the problem, he's free falling until he hits the giant airbag. And then he's going to slow down to a stop in the airbag. The beauty is we don't need to know how the airbag works. We just need to know how much braking distance did it give him. We need to slow him down, not so fast that the acceleration kills him. So the problem will break nicely into two. The falling part is the first half. And what do we need to know? Well, he's going to hit the airbag with a speed and come to a halt. What's the speed he's going to hit the airbag with? Well, that would be his final speed when he strikes the airbag. So we set up an equation. We know the height of the tower and he's falling. We don't know and don't care about time, allowing us to use this dear friend again. And when we're done, we get VF as the root of 2AD. We plug all our numbers in, and he hits the airbag at 44 meters a second. Problem is over. Now at this point, a new problem begins. So the final velocity at the end of the first phase now becomes the initial velocity at the slowing down phase. So now the 44 meters a second is the starting velocity when he hits the bag. Now he took 200 meters to fall and he reached 44 meters a second. That happened at 1G. Do you understand that if we stop him in a distance that's 10 times shorter, his slowing down acceleration would be 10 times gravity? And once we go much past 10 times gravity, we're talking about injury. Do you have to memorize that? No, but you'll wind up learning it by the end of the course. You hit 30 Gs, he's not leaving the area except in an ambulance, and he may not be back. So we take these, put them in, and we're going to keep acceleration below 10 Gs. That's what I meant by here. I was running out of space. So we don't want to order up a number 10 Gs for acceleration. We want to calculate it and make bloody sure it's under 10 or the stuntman's going to get injured. So once again, we don't have time. So we're back to the same formula, and what we get is about 10 meter thick bag. Doesn't matter what's in the bag. The bag is going to collapse when he hits it. You've probably seen people jumping on those bags. You hit them, and the side bursts open and lets the air out, and the bag deflates. So if this bag brings him to a halt in about 10 meters, that will keep his acceleration underneath the critical threshold of 100 meters a second squared. So what I did is I took 10 times gravity, I put it in there, and this means for a 10 times gravity deceleration, the bag would have to be 9.7 meters thick. Now, is that the bag's minimum thickness or its maximum thickness? And again, you don't have to worry about how the bag works. You just need to know the bag must retract almost 10 meters when he hits it, so his slowdown is not too violent. Okay? These ones are really good problems. This one is likely to show up on a test as one of the higher end problems, not an easy problem. This would be in the 80% and above category. Okay? You would only see like one, or I might put it in a multiple choice and make you work for that mark. So that is the end of a whole series of decision-making problems. I hope you enjoyed it, like a root canal or a court trial to the death penalty. But anyway, hopefully this helps you make those decisions that are the real critical key, not the actual arithmetic.